Hi guys, how are you all doing? I hope you are all doing fine. So, it's been a very long time since I actually picked up on the lecture that I left you with. I was just busy with my work, and today is Sunday, so I have all the time to myself. I also have an exam coming on 2nd of December. I'm really not that worried about it because I might even skip it. It's not that important. It is like an internal assignment exam. So, enough about me. We will just start from the lecture I left you with. I think uh, I introduce you to the fact that what are irrational numbers. We have done some exercise. I think exercise 1.1, we have done some questions. And there was this particular question where uh, three of the students were in the circle. Sorry, two of the students were in the circle. And the time one requires to complete one circle around the circumference of the circle was, I think, 18 minutes, and another student took to cover the same distance, the circumference of the circle, in 12 minutes. And we have to find out that when will be the first time they will meet again. If they start from the same starting point, what will be the time when they will meet again at the starting point? So what we have to do, I think. We assume that let x be the time when they will meet again, then obviously they have to cover one complete circle. So whatever x is, it is a multiple of 18. Similarly, x is also a multiple of 12. So 18 divide x and 12 divide x, that would simply give us the idea that both 18 and 12 are dividing. So if 2 is dividing 6 and 3 is dividing 6, then 6 is the LCM of 2 and 3, right? So what we have to do is we have to find the LCM of both 18 and 12. And I think the answer was 18 and 12, right? I think 9 twos are, and then there was 2 ones are and 2 six are, and then we have to do 6. I think 3 fours are, then 3 six are, then 3 twos are, and here is 4, then 2 ones are and 2, so it's 4 multiplied by 3, that's 12, and 12 multiplied by 3, I think 36. I think the LCM was 36, and we found out that at every multiple of 36, that is 36, then 72, and I think after that they will meet again at the starting point, but we have to find out when they will meet at the starting point for the first time, then the answer would be 36. I could not recall it completely, but I think this is what I left you with. Today, we're gonna start with a much more better topic. I think today we're gonna start with there are two theorems, and there is very interesting concept of how to prove root 2 and root 3 as an irrational numbers. So let me just start. Okay, so I think, yeah, it is recording. Let me jump to the tab. So yeah, revisiting irrational numbers. We have to prove all of this is irrational number. Quick revision. Irrational numbers are the numbers which are either they are non-terminating and non-repeating numbers, or simply are numbers which can't be written in the form of p divided by q, where p is an integer and q is a natural number, and obviously because q is a natural number, it can't be 0. So let's just start with theorem 1.2. It says let p be a prime number. If p divides a square, then p divides a, where a is a positive integer. Okay, so I think we're gonna switch color to this bright green color. Alright, okay, I forgot to wear my glove today, but let's just see. The theorem is, oh no, if p, where p is a prime number, divides a square. This is the symbol for division. So if p divides a square, we're gonna write it like this. You don't have to remember the symbol. If p divides a square, then p divides a. This is the theorem, and we have to prove this. So let's just assume, because suppose A is a natural number, right? So either it is gonna be a prime number or composite number, right? Or either it is gonna be 1, right? So it can either be 1, a prime number, or a composite number. Whatever it is, suppose uh, A is 1. So if A is 1, A square is also gonna be 1. But then there is no prime which divides 1, right? Because the only number that divides 1 is 1 itself, and 1 is not a prime, so A can't be 1. Suppose A is a prime number. Let us just say A equals to 2. So if A equals to 2, if A equals to 2, then A square is gonna be what? 2 square, which is equal to 4. If we say P is dividing A square, that is 4, then what are the possibility of P? P can either be 1, it either can be 2 or 4. There is no other number other than 1, 2 and 4 that can divide 4, right? How I know this? Because if a number divides 4, that means that when I multiply this number with some natural number, I'm gonna get 4. So if I multiply 1 with 4, I'm gonna get 4. If I multiply 2 with 2, I'm gonna get 2. And if I multiply 4 with 1, I'm gonna get 1, right? So now, if the possibility for P are either 1, 2 and 4. If P equals to 1, then again, sorry, if P equals to 1, then because P has to be a prime number and P1 is not a prime number, that would give us the idea that P can't be 1. So out of the 3 possibility, P can't be equals to 1. If P is exactly equal to 2, then this is a possibility, right? Because 2 itself is a prime number and 2 divides 4. If P equals to 4, then you will notice this idea that 4 do divides 4, but 4 itself is not a prime number, right? That means this is also not possible. So the only possibility for P is equal to 2. So if 2 divides 4, then obviously 2 divides A. A here is 2, which is true, right? So the theorem does gives this implication. This is the sign of that if this statement is true, then this will imply this statement, right? So this was a simple example of what if A is a prime number. Now suppose A is not a prime number, A is a composite number, and I'm taking any general composite number. So I can write A like this. Suppose, because A is a composite number and we have already have learned about the fundamental theorem of arithmetic, that every composite number can be written as product of prime numbers in a unique way if the order in which the prime numbers are chosen doesn't matter. So if A is a composite number, I can write it like this. Suppose P1, P2 up to Pk. So this is product between P1 and P2. And this dot simply means that there are other primes in between them. For example, P3, P4 up to Pk minus 1 and then Pk, right? Suppose the prime factorization of A is like this. Then A square is gonna be what? This multiplied by this. So if I'm multiplying P1, P2 up to Pk, 2 itself, then what I'm gonna get? P1 square dot P2 square dot Pk square, right? For example, if I have to multiply 2 and 3 by 2 dot 3, what I'm gonna get? Because this is all simple multiplication, and ordinary multiplication allows us to choose any two number to multiply first. Like the order in which the multiplication occurs doesn't matter, right? So I can choose to multiply 2 and 2 first, and then I can choose to multiply whatever the resultant is to the resultant of 3 multiplied by 3. So I'm simply gonna get 2 square, and here I'm gonna get 3 square. This was just an example, right? So I have chosen A to be P1, P2 up to Pk, where all of these are prime numbers, and this is basically prime factorization of A. So A square, by application of this simple example, it is going to be like this. So if I'm saying that P divides A square, now what does this actually mean? When I say P divides A square, what does it actually mean? It means that because P is a prime number, then A square, when written as product of prime, P is one of those primes. If you could not understand what was my statement, I'm going to explain it to you in a simple language using an example. Suppose A is equal to 2.3. Then A square is going to be what? 2 square dot 3 square. Now, suppose we have to choose a prime number that divides this A square. So suppose 2 divides A square, which in this case is 2 square dot 3 square. So because this 2 divides this number, this A square, when this A square is written as in prime factorization form or as a product of prime, you will notice that this 2 is one of the primes. When it is written in the form of prime factorization, it is one of the prime, because you can easily see that when I write A square as 2 square plus 3 square, 2 is one of the prime. And you will also see that the only number that actually divides 2 square and 3 square are either 1, 2, 2 square, or 3, 3 square, or 2 multiplied by 3, or 2 multiplied by 3 square, or 2 square multiplied by 3, and 2 square multiplied by 3 square. Only these are the natural numbers that actually divides A square, in this case 2 square multiplied by 3 square, and out of which only this and this are prime numbers. Every other is a multiple of either 2 square, 3 square, or 2 multiplied by 3, which itself contradicts the definition of prime number, because it has more than one factors. 1, 2, 3, 6, right? So it has more than one factor, so it can't falls in the category of prime number. Same goes for this, and same goes for this. So this is what it lacks, and yes, I'm gonna simply take a break. Okay, so continue from this point on, we can easily see that all of these numbers are now gonna be prime numbers. So the only number that divides A square is either 2 or 3 if this number has to be prime, right? So coming back to the question, if P divides A square, then P has to be one of the prime numbers. When A square is written as prime factorization, it has to be one of the prime. That means because A square equals to P1 square, P2 square, up to Pk square, and P has to be one of this, then one of this, it simply means that P is either P1 or P2, P2 or P3, or the choices are up to Pk, right? So if P is one of P1, P2, P3, that would means that because A can be written as P1 dot P2 dot P3 dot up to Pk, and P is one of it, then because this is written as P multiplied by P1, I'm assuming let P equals to Pi, right? So I can because this is all simply multiplication, I can choose to take P first and multiplying with the rest of the uh, resultant formed by the product of this. So I will simply get P2, and there will be Pi minus 1, and there has to be Pi, right? But I have taken Pi here and renamed it as P. So I can simply get rid of this, and the after Pi the prime will be labeled like Pi plus 1, and then we will go to Pk. So because A can be written like this, and because A is simply P multiplied by this, that means that P times of some natural numbers is actually equals to A. That would means that if I divide this side by P, I have to divide this side by P2, but P and P will get cancelled, and here I will have this natural number. Because A divided by P is actually equals to natural number, that means P divides A, right? So I think this was our theorem 1.2. Let's just move on to theorem 1.3. Root 2 is an irrational number. We have to prove this. Okay. So let's just simply prove that root 2 is irrational number. So when I actually define irrational number, and I given you some examples like root 2, root 3, pi and e, I simply told you that for now you have to just try to remember them, that they are examples of irrational number, and I'm going to prove it later in the video. So this is the moment I'm going to prove it. So root 2 is irrational, we have to prove. So okay, let me give you an intuition of how I'm going to do it. This is one of the most important methods that we use in mathematics to prove something. The method is called proof by contradiction. And I'm going to give you an example so you can actually understand what we are going to do here. Suppose, again, the same example I took a long time ago. Suppose you have a bag and there is an apple and orange in it, right? So there are only two possibilities. If you if you try to pull one of the things out of the bag, there is only two possibility, that either the object is going to be apple or the object is going to be orange. So suppose you have a bag, it has an apple and orange in it. If you put your hand into it and took one without looking at what you are actually grabbing out of it, you just pull one of the object out of it, right? So if the object that you pulled out of it is an apple, can you tell me what is left in the bag? Orange, right? Because there is only two possibilities. If what you have in your hand is an orange, then only apple will be the object that is left in the bag. And if the object in your hand is an apple, only orange will be the object that is left in the bag, right? So if you only have two scenarios, and if you have somehow proved that one of the scenario is not possible, then the second scenario is obviously gonna be the obviously gonna be true, right? Suppose there are only two choices, and you have proven that one of them is false, then the other one has to be true. Because if other one is not true, that means that that object is neither any of and both of them, right? And if that is the case, okay, I have to plug my laptop to the charger. Mm, and just wait a minute. Okay, I think it is charging now. Yeah, it is. So what I'm simply trying to tell you is, if there is only two possibility, and it is also sure that one of them has to be true, right? And if you have somehow proven that one of them is not true, then you don't have to prove the other one, because the other one has to be true, obviously, right? So this is what we're gonna do, because root 2 root 2 is a real number, because the value of root 2 is something, I think 1.4 something, and obviously because it is an irrational number when it is expressed in the decimal expansion form, this expansion is going to be non-terminating and non-repeating. But because this number lies between 1 and 2 on real number line, this is a real number. So if root 2 is an irrational, if root 2 is an real number, then we knew the definition of real number. Real number is a collection of all the rational and irrational number. That means, and we have also proven that a number is either rational or either irrational. A number can't be both, right? So root 2 is either rational or irrational. It can't be both and it can't be none, because it is a real number. And how I know it is a real number line? How I know it is a real number? Because the value of root 2 is gonna be 1.4414, something like that. And because this number lies between 1 and 2, then this number is definitely gonna be a real number. So root 2 is either irrational or irrational. We have to prove that root 2 is irrational. What I'm going to do, I'm going to simply prove that root 2 is not rational. So if it is not rational, it has to be irrational, because there is no other choice. Right? So let me simply prove, let me assume first, let root 2 is rational. If root 2 is rational, by the definition of rational, root 2 must be of the form p by q, where p is integer and q is natural number. But there was also one of the most important, I think, what should I call it, property to this, that like 2 upon 4, this is a rational number, right? Because this is an integer and this is a natural number. But this 2 upon 4 can be written as 1 by 2. Now obviously both of them are equal, so I can use either one of them, but we're going to use this form here. Why? Because if you look closely enough, this, when I write 2 upon 4 like 1 upon 2, this form gives me the property that 1 and 2 have no common factor other than 1. Both of this does not have any other common factor other than 1. So only 1 divides 1 or only 1 divides 2. This is the only common factor both numerator and denominator has. But when I'm looking at 1 by 2 in this form, 2 and 4 have 2 as a common factor and 1 as a common factor. So I'm gonna write, if even if root 2 is written as p by q form, I'm gonna make sure that this p by q form is such that both of them, numerator and denominator, doesn't have any other factor other than 1 in common. And when this condition occurs, that both numerator and denominator doesn't have any other doesn't have any number other than 1 as a common factor, we call them co-primes. So co-prime is the property of two numbers if they doesn't have any other common factor other than 1. So I'm going to write root 2 is equals to p by q, where p and q are co-prime. Both of them are co-prime, right? Don't get too confused with the definition. Simply think of it as, suppose when I say root 2 is equals to p by q, I can simply write p is 2 and q is 4, right? So this is also true. When I'm writing simply this part is also true. But I want this part to be like this in this form. And to get to this form, I have to put another conditions that both p and q has to be co-prime. So now, let's simply do, because this is equal to p by q, and because root 2 is something that is going to be difficult to calculate, what I'm going to do is I'm going to get rid of root 2. And the simple method to get of root 2 is by squaring it. So what I'm going to do is I'm going to multiply q both sides. If I multiply q by both sides, I can cancel q and I will get 1. Because q1s are q, right? So I can divide q by q itself, and what I'm going to get 1. And 1 multiplied p is equals to p. Now q root 2 is equals to p, and I have to get rid of the square root, so I'm going to square both of this side. Now this is also one of the property that if right hand side is equal to left hand side, then squaring it also holds the equality. That means that if a equals to b, then a square equals to b square. This is true. So if this will imply this, right? So because this is equals to this, their square is also going to be equal. So q root 2 square will be equals to p square. Now q root 2 square is going to be q square, and root 2 multiplied by root 2. Now you can look at root 2 multiplied by root 2 as 2, or you can think of it as like this. You can either look at this, the root 2 and root 2 is going to be 2. In general, root a multiplied by root a is always going to be a, right? Obviously, if both of them are natural numbers, even if they are integers, this is going to hold. So either you can look at the this is square of root 2 like this, or you can either look at this in this way, that suppose a has a power p and we are squaring it, we are raising its power up to q. So this simply equals p multiplied by q, right? In the same manner, if I have to square root 2, then because this itself is 2, this simply means power raised to the, this simply means the number is raised to the power 1 by 2, right? So root 2 will simply means 2 raised to the power 1 by 2, and squaring it simply gives us this 1 by 2 multiplied by 2. So 1 by 2 multiplied by 2 is gonna be what? 1. So this is equals to 2 to the power 1, that is equals to 2. So I'm gonna simply write here multiply by 2, and p square is going to be like this. Now, if you look closely now, left hand side has 2 as a multiple. That means we can divide this side by 2. And if we can divide this side by 2, we can also divide, we also have to divide right hand side by 2. Because 2 will get cancelled with 2. That means this side is divisible by 2. Because when I divide this number by 2, I'm getting a natural number, right? That means this number is divisible by 2. So this number has to be divisible by 2 too. So assuming that 2 is dividing p square, where p is an integer. So, and 2 is a prime number. So by previous theorem, we knew, right, that if p divides a square, where p is a prime number, then, and a can be any natural number, then p divides a, right? So if 2, where 2 is a prime number, divides p square, then 2 must divide p. And if 2 is dividing p, that means p can be written as 2 multiples of something. We don't know what natural number it would be, but p can be written like this, right? That means that p has 2 as a factor. Now, because p can be written like this, let us just say that p is actually equals to 2 times of, let us assume u, where u is obviously a natural number. Suppose p equals to 2u. So I'm going to put this value of p into here in this equation. So what I'm going to get, q root 2 square equals to p square, but p square is simply going to be 2u square. So what I'm going to get, okay, the page is over. Let's just move to the next page. Okay, and let me just switch to the color yellow. Okay, so we were q root 2 square equals to 2u square, right? So this is going to be again 2 square and 2, and this is going to be 2 square, that is 2 square and u square. Now this number is divisible by 2, because if I divide by 2, I'm gonna get q square, which is a natural number. So this digit is divisible by 2. So because this is equal to this, so this number must be divisible by 2, which is true, right? Now I'm gonna get q square equals to 2 times of u square. Because this number is divisible by 2, so it has to be divisible by 2 because both of them are equal. That means 2 divides q square, where 2 is a prime number and q is a natural number. That would give me the idea that 2 must divide q2. That means 2, or I should say that q can be written as 2 times of something. I don't know what this natural number will be, but q can be written as 2 times of this. That means what? That means that both p and q has 2 as common factor. But we assume now that p and q both are co-primes. That means they don't have any other number other than 1 as a common factor. That means whatever we have assumed, and assuming that to be true, whatever we have concluded gives us the contradiction of what we have assumed. Right? We assume that p and q are co-prime, but we have simply proved that p and q has 2 as a common factor. That will contradict the definition of co-primes. That means that this is the symbol of that is simply a mathematical is simply uh, English letters, English words, okay? But we simply use this sign in mathematics to write it in the short form. So that is our assumption, whatever we have assumed, our assumption is wrong. So our assumption was wrong. So what we assumed? We assumed that root 2 can be written as p by q when p and q are coprimes, but we can't write it like this. That means that root 2 is not equals to p by q, where the usual definition, p is an integer, q is a natural number, and p and q are coprimes. That means that root 2 is not rational. And if root 2 is not going to be rational, root 2 is irrational. So that is, I think, that is all for the proof. And that is all gonna be today's class. I hope you enjoy it, and I hope you will tune in for the next class. Thank you. And please do subscribe.